Research on engineering performance reveals a stark bottleneck. The ability to analyze a complex problem and generate a viable solution is driven roughly 20% by domain knowledge. The remaining 80% relies entirely on the cognitive frameworks you use to think. The scale and complexity of the systems engineers design today, from automated manufacturing grids to heavy propulsion systems, require flawless logic. Domain knowledge, like thermodynamics or material science, is only the raw material. Analytical thinking is the machine that turns that material into a working solution. Yet most engineers fall into the tool trap. Confronted with a failure, they immediately reach for their most advanced tools, firing up CAD software or running a computational fluid dynamics simulation before they have accurately defined the problem. This happens because they are operating at the wrong layer of the cognitive hierarchy. Problem-solving performance is governed by a strict 5-tier structure. Most engineers jump straight to Tier 4, software and tool proficiency, ignoring the foundational levels of analysis entirely. Applying advanced simulation software to a bad assumption only generates an elegant, high-resolution solution to the wrong question. Constructing that capability requires building the analytical engine from the ground up, starting at the base. The highest return on your cognitive investment happens in Tier 1 and Tier 2. This begins with epistemic honesty, the strict discipline of admitting what you do not know, seeking hard evidence, and clearly framing the actual problem before proposing a single solution. Take a heavy marine engine. If tasked to improve the efficiency of its fuel injection system, the standard engineering impulse is to look at the existing injector and attempt an incremental tweak, perhaps altering a nozzle angle or adjusting spring tension. First principles thinking strips that convention away entirely. It forces you to ignore how the component is currently built and instead isolate the irreducible physical laws governing the system. You stop asking how to improve the injector and ask, what do the laws of thermodynamics actually require for maximum combustion efficiency? What does ideal fuel delivery physically look like regardless of the mechanism? Once you establish that physical truth, you move up to Tier 2, systematic decomposition. You break this newly framed problem down into strictly bounded sub-problems, isolating fuel pressure, droplet dispersion, and timing. Here, you execute constraint identification. You explicitly divide your variables into 2 distinct categories: the fixed laws of physics that cannot be broken, and the conventional design choices that can be changed. Rigorously decomposing a problem into its physical constraints eliminates conventional dead ends early. By isolating the exact variables that can change, you define the path to a solution without wasting resources on impossible designs. With the problem structured, we arrive at Tier 3, methodology. This is where you map the causality of a failure. The most common cognitive error here is treating the first visible symptom as the actual root cause. Formal root cause analysis forces you past the surface. You can approach this inductively from the bottom up, using a failure mode and effects analysis to track how a single component's breakdown impacts the whole. Or you can work deductively from the top down. This top-down approach is a fault tree analysis. It places the major failure at the top and maps every logical combination of events that could trigger it, tracing through rigid and/or logic gates until isolating the exact origin of the breakdown. But linear root cause analysis has a blind spot. Most modern engineering challenges, like process plants or complex propulsion systems, are not isolated events. They are dynamic, interconnected system behaviors driven by continuous feedback loops. Systems thinking trains you to look for emergence and delays. When a time lag exists between an input and a physical effect, an operator will often assume the system hasn't responded, prompting a second input. The accumulated inputs then hit the system at once, causing violent oscillation. If you apply a linear methodology to a dynamic system, you will misinterpret a balancing loop as a mechanical failure, and your intervention will guarantee a disastrous overcorrection. The analytical tool must match the physics of the problem. When it comes to generating solutions, unstructured group brainstorming consistently fails. Cognitive research shows it produces fewer, lower-quality ideas due to conformity pressure and evaluation apprehension. Engineering requires structured, algorithmic creativity. As matrix, you map the overall weight of the moving object. Where those two parameters intersect, the matrix provides a specific set of numbers. These correspond to the 40 specific inventive principles that have historically solved this exact structural conflict in completely unrelated industries. This pairs directly with constraint relaxation. You define the ideal final result, where the system achieves its function with zero cost and zero complexity, and work backward. You quickly discover that constraints you assumed were physical limits are actually just conventional habits. Engineering creativity is not a random spark of genius. It is the output of a highly structured algorithm of contradiction resolution, narrowing the vast solution space into precise, proven directions. Even with perfect frameworks, analysis occurs inside a human brain. Cognitive science identifies two modes of thinking, and the fast automatic pattern recognition of System 1 actively degrades logical engineering analysis when faced with novel problems. These biases are active hazards. One of the most destructive is functional fixedness, the inability to see a component outside of its traditional role, which completely blocks creative solutions. Consider a famous manufacturing case where empty soap boxes occasionally slipped past the filling station on a conveyor belt. A team of engineers spent weeks designing an expensive, complex X-ray scanner mechanism to detect them. A factory worker solved the same problem by placing a cheap industrial fan next to the belt to simply blow the empty boxes off. The engineers saw a fan only as a cooling device, not a mass sorting mechanism. To defend against biases like this, you must build a library of mental models, compressed representations of how systems actually work. One of the most powerful is inversion. Popularized by Charlie Munger, the rule is to work backwards. Instead of asking how to make a design succeed, you identify every specific condition that would guarantee it fails. You eliminate those failure states first. You follow that immediately with second-order thinking, asking, "and then what?" after every proposed fix. The quality of an engineer's judgment scales directly with the library of mental models they carry to defend their own logic. The final tier of the hierarchy is habits. This is the multiplier. Everything below this tier is additive, but deliberate daily practice produces an exponential return on your analytical capability over time. We often mythologize expert intuition as an innate talent. In reality, expert intuition is simply fast System 1 pattern recognition that has been rigorously trained by thousands of slow, deliberate System 2 practice sessions. You build this through a targeted daily regimen, 10 minutes structuring and decomposing a complex system, 10 minutes mapping causality with the 5 whys, and crucially, 5 minutes logging your own reasoning errors to track where your assumptions break down. The engineers who became legendary problem solvers were not defined by magic. They were defined by extraordinary analytical rigor, epistemic honesty, and the habit of thinking carefully about their own reasoning. Engineering thinking is a trainable skill. Frame first, contradict with trizz, invert your logic, and do the daily work. That is how you build an analytical engine that compounds with the complexity of the challenge.